If you have a really slow function, like a function to find prime numbers, and you want to make it run faster, you can use native code, a way to run C++ directly in your Node applications. To get started, run npm install -g node-gyp, which is like GCC, but specifically for Node. Follow the additional installation instructions for your operating system. In your npm project, run node-gyp configure, which runs into an error which states that you need to create binding.gyp first. Create binding.gyp, where we will specify our export targets, and create an export called findprimes. From the source findprimes.cc, our C++ file. Now create findprimes.cc, and we can run node-gyp configure again, which we can try to build with node-gyp build, which compiles the code into binaries at build/release, which directly can be imported into our JavaScript code. However, when we try to import it, we get an error. To register our module, we need to include the Node API header file. Your editor may throw an include error, but still be able to compile it. In Visual Studio Code, you can fix this by going to Quick Fix, edit include path settings, find where node-api.h is stored for the version of Node that you wish to compile for, and add it into your include path. Next, to register the module, we run the function napi module, naming it with the module name we declared earlier, and providing it with an init function. Next, we need to define the init function, from which we want to return a napi value. Napi values form the backbone of all variables in Node.js. In your C++ file, JavaScript strings, numbers, booleans, and functions are all represented with napi value. The init function takes in a napi env and a napi value. Create a new napi value representing our findprimes function, and return it. Now, if you try to console log the value, you'll find it returns a value that makes no sense. You can instead make it into a function using napi create function, providing the C++ native function we wish to bind, and the memory address of our returned value. We now define the function itself, which takes in the environment and a callback info. We can extract the arguments passed to the function using napi get callback info, passing in the expected number of arguments and an array to store the arguments in. Next, we can convert the argument provided into an integer, napi get value in 64. Then we can get the largest prime below that value with the function findprime, which we will implement later. For now, let us just return the value passed in, and convert it back into a JavaScript value with napi create double, and return the value. Now, if you build the file and pass a value to the function, it will return the exact same argument passed to it. Finally, we can implement the findprimes function, the code for which is available in the description below. And now you can test the speed of the various functions. As you can see, the native function performs way better for smaller input values. And if you want to know more about the performance comparisons, fhinkel has done some great comparisons of the speed differences, so do check his work out. The final thing to take note of is that there is no input validation, and your code will still run despite there being blatant errors. To fix this, we can define a wrapper function napi call, which you can find in the description below, and use this when calling all of your napi functions. And now when you run the code, it will throw the appropriate errors. That's cool and all, but if you are interested in a backend framework that is simple to set up and ready to scale, you can check out EzBackend, the backend framework we are working on. Also, if you have any video or tutorial requests, do let us know in the comments down below.